I would like to welcome you to the first annual memorial lecture in honor of Svetlana Chernikova. I'm Robin Marsh. I'm the co-director of the Beers Environmental Leadership Program and a dear friend of Svetlana. As I'm speaking, you will see a beautiful slideshow of photographs of Svetlana that was put together by the ELP. Come. Don't be shy. Come up front, Maria. We're all informal here. And it was also put together by her husband, Dmitry Slaviskaya. I think that Svetlana's great love of life and people come through these photographs, as well as her passion and accomplishments as a scholar, advocate, and sustainable development leader in Russia. As you will note in the program, I hope some of you were able to get these. We met Svetlana, who was professor of geography and geoecology at St. Petersburg State University, for the first time when she was a participant in the 2003 class of the Beers ELP here at Berkeley. Several photographs of her show her with ELP classmates. Less than 10 years later, in August 2011, Svetlana died at just 48 years old of a rare form of cancer. She has a very accomplished grown son, Arthur, and her husband, Dmitry, a professor of biology at St. Petersburg State University. Upon Svetlana's death, Suzanne Campbell, who unfortunately can't be here tonight, but she's here in spirit, she was the board director of the Global Fund for St. Petersburg State University and enabled the transfer of nearly $50,000 to the ELP to establish the Svetlana Chernikova Memorial Fund. This fund will support a range of activities to carry on Svetlana's legacy of sustainable development leadership, both in Russia and Berkeley. We hope to grow the fund substantially over the next few years. A couple of minutes to tell you about Svetlana's most important accomplishments, and then I will turn the podium over to our first Svetlana Chernikova ELP Fellow, Angelina Davydova, and then to our keynote speaker, Dr. Fritjof Capra. Upon return from the ELP in 2003, Svetlana coordinated the first ever interdisciplinary center at St. Petersburg State University, creating with 13 different academic departments the Center for Cooperation on Sustainable Development and Environmental Leadership. Inspired by the ELP, the center offers short courses on environmental leadership and systems thinking to young faculty, government officials, and civil society organizations in Russia and the region. Under Svetlana's leadership, the center created an interdisciplinary master's program in sustainable development and ecological management, and a few years ago was appointed Vice Dean of International Education Projects. Svetlana also was the founder of the NGO Local Agenda 21 and Youth Creative Initiatives, and she worked with the Ecological Footprint founder Matis Wagernakl to found and coordinate the Russian node of the Global Footprint Network. Svetlana also led participatory field research and provided technical support for many local sustainable development projects in the northern territories of Russia. She published several papers on the ethno-ecological approach to sustainable development of the indigenous peoples of northern Russia. And in the last few years, Svetlana developed a new academic department of environmental health and public access to health information at St. Petersburg State University, with the support of environmental health professionals at UC Berkeley, Stanford, the Kaiser Foundation, and the US EPA. We are very gratified to learn from Svetlana's husband, Dmitry, that her work and legacy continue on at St. Petersburg State University and beyond with a wide range of academic, NGO, and international partners. To conclude, I must tell you that Svetlana's life and work were profoundly influenced by our keynote speaker, Dr. Fritjof Capra, and in particular, his pioneering work on systems thinking and deep ecology. one of the high points of her life was meeting Fritjof in person on her last trip to California in 2009. She could barely contain her excitement, and today is surely with us, smiling, and will be listening attentively to his lecture on systems thinking and sustainability, contributions from Russian scientists. Now, this session is being videotaped so that we can share it with Svetlana's colleagues back in Russia, and they have already said that they're going to be having subtitles in Russian so that language will not be a barrier, and we will share it with the youth environment movement that is emerging in Russia as well. First, even before Fritjof comes up to address us, I'd like to introduce you to an environmental journalist and SPSU journalism faculty member, Angelina Davydova, who is, as I said, our first Svetlana Chernikova Fellow to the ELP. Angelina has been covering exciting changes occurring in Russia today with the youth-led community and environmental movement. She will speak briefly on this topic, and then we will hear from Dr. Capra. So thanks very much for joining us tonight, and after this lecture, which Fritjof wrote especially for this occasion, and it's an original piece of work, please join us in a reception and a light dinner outside. So thank you very much.
Good evening, dear ladies and gentlemen. My name is Angelina Davydova, and I come from St. Petersburg, Russia, from the St. Petersburg State University, just like Svetlana Chernikova. And I'm very happy to welcome you here tonight. Although I didn't know Svetlana Chernikova personally, since I joined the St. Petersburg State University only a year and a half ago, I can certainly certify that all her work, all her activities, all her research is proven to be extremely important for everything which is now being done, not only at the St. Petersburg State University, but in Russian academic circles in general, across the bigger cities. So you can really come across her name in wherever you start reading something on the issue of sustainability in Russia and global aspects of sustainability, global agenda of green economy. So even though Svetlana Chernikova is unfortunately not with us anymore, her work still lives us and proves to be and provides a very significant impact on everything which is now being done in Russia. And here I would like to say just a few words to give you a brief picture of the whole sustainability discourse, both at the state level and the informal level, currently in Russia. So you might have read about it, or you might have seen it on TV, in American press, and online media, that the whole discourse of sustainability and environmental issues is not really common in Russia very easily and very quickly, as one may expect with the recent economic development of the country. There are a few reasons to it. One of the reasons is that our economy is mostly resource-based and is based mostly on exploitation of raw resources and quick exports of them. And when I just bring up a few figures that in the recent 5 years, the effect of exploitation of raw resources and their exports has been up till 70 to 80% in the federal budget, in the income of the federal budget of Russia. You can obviously see that in such a situation, it might not be that easy for environmental issues to come in place. Another problem which I quite often come across is that Russia, being such a vast country, and not so densely populated, it may be one of the least populated countries on the world. It's also true that quite often environmental issues don't come as obvious and are not so easy to be seen and spotted as in many other regions of the world. So that is another challenge for many environmental activists trying to work with the issue, trying to promote sustainability discourse in Russia. So even though in the latest years, since the fall of the Soviet Union, we had this whole agenda that first comes the economic development, and only then we can think about environmental issues and social issues. There are, however, a number of people, and this is a growing number of people, all across Russia, who are becoming seriously concerned with both environmental situation in Russia, social inequality, regional inequality in Russia, which you can really observe throughout all of the country. And interestingly, most of these protests come in big urban centers like Moscow, St. Petersburg, Novosibirsk, Ekaterinburg, and other cities, I would say, above 1 million of inhabitants. And it's quite often that they come first with also issues of urban ecology. For example, well, a new road has to be built, big, at the beginning very small, but then a bigger protest group is being built in order to fight for it. And some of these cases have been really successful. Like, to name the most recent one, which you might have also got in the international media, was the Heimki forest movement, which originated 2.5 years ago, when a small group of environmental activists in the small city of Heimki, to the north of Moscow, have set up all Russia, and even, I would say, an international campaign for the support to keep their forests. So such groups appear regularly in various parts of Russia. Another really big environmental movement is connected with the recent developments in relation to the Olympic Games, which are due to be held in Sochi, that's in south of Russia, in 2014. And you can really see it's like it's in the south, and then also further environmental groups trying to protect one of the largest freshwater lakes on Earth, Lake Baikal, all the way to the west in Siberia. So this is like one direction. The protest actions are growing, young people are getting attached to it, they're getting engaged in it, they're very actively using social media, they're using international contacts. Yeah, and another direction of environmental activism, which has been particularly interesting in Russia in the latest years, also comes mostly among young people and mostly among like large megapolis areas of the country. And they're usually connected with the areas where the state fails to fulfill its function as an environmental regulator, where state doesn't really provide an adequate legislative framework, organizational framework, administrative framework for some specific environmental-oriented activities to be implemented. To speak of, we really don't have a separate trash selection in Russia. So there are a growing number of groups who do it on their own, who organize it in their own community, who organize it in their own city, in their own part of the city, and these groups are growing. Or other groups who are trying to solve the problem of trash run in our parks, in our forests, on our seasides and lakesides, and or other groups which are really very much connected and really much concerned with the issue of green consumption, of promoting environmentally friendly ways of living, alternative systems of living, promoting things like car sharing, free markets, when people just exchange goods and clothing and books and whatever, which you don't need anymore. And so all these things, all these areas of new thinking, all these areas of other development, as Professor Capra keeps telling us about. And so this is all indeed happening, and this is a very interesting change of predominantly awareness and predominantly consciousness, which is happening in people's minds and in minds of many young people all across Russia. So with this, I would, at this very point, I think I would finish, but I would be really happy to answer any further questions of you on the current development of environmental awareness and environmental movements in Russia. And I'm very much looking forward to Fritjof's lecture at this very moment. So thank you very much, and I hope you enjoy the evening tonight.
Good evening. I'm very honored to give this first Svetlana Chernikova Memorial Lecture and I'm also very moved by the occasion. I love teaching in the BS Environmental Leadership Program. This is my 3rd year, and I came to the ELP in a way because of Svetlana. As you heard, she visited here in 2009 and wanted to meet with me, and she actually contacted our friend Miguel Altieri and asked him to contact Robin Marsh to arrange a meeting, and this is how it happened. And this is how I met not only Svetlana, but also Robin, and a year later I joined the ELP faculty. So in a way, I owe all this to this connection to Svetlana. As you have heard, she was an accomplished ecologist and systems thinker, and as such, she followed a long Russian tradition. To honor her, I want to show you why systems thinking is crucial for building a sustainable future and how it emerged and evolved in Europe in the 20th century. And I want to highlight the significant contributions to this intellectual movement from Russian scientists and philosophers. Well, let me begin with sustainability. As you know, the great challenge of our time is to build and nurture sustainable communities, that is, social, cultural, and physical environments in which we can satisfy our needs and aspirations without diminishing the chances of future generations. Now, this is the sort of classical definition of ecological sustainability introduced by Lester Brown in the early 1980s. And since that time, the concept of sustainability has often been distorted, co-opted, and even trivialized by being used without the proper ecological context. A good example is the agreement signed just a few weeks ago, by world leaders in the Rio +20 conference. When you followed the document through its preparatory stages, you could see that the first draft began with sustainable development. This was changed to sustainable growth in subsequent drafts, and in the final document, you read about sustained growth, which, of course, from an ecological point of view, is manifestly unsustainable. What is sustained in a sustainable community is not economic growth, but the entire web of life on which our long-term survival and well-being depends. In other words, a sustainable community is designed in such a way that its ways of life, its businesses, technologies, social institutions, and so on, do not interfere with nature's inherent ability to sustain life. And the first step in this endeavor, naturally, needs to be to understand how nature sustains life. And it turns out that this involves a new ecological understanding of life and a new kind of thinking in terms of relationships, in terms of patterns, in terms of context. And indeed, such a new understanding of life has emerged over the last 30 years, and much of what we teach at the ELP are various parts of this new understanding of life. Just to sum it up, at the forefront of contemporary science, the universe is no longer seen as a machine consisting of several elementary building blocks. We have discovered that the material world ultimately is an inseparable network of relationships, patterns of relationships. We have also discovered that the planet as a whole is a living, self-regulating system. The view of the human body as a machine, held by Descartes and scientists and philosophers centuries after him, and of the mind as a separate entity is now being replaced by one that sees not only the brain, but also the immune system, every single tissue, and in fact, every single cell of the body as a living cognitive system. Evolution is no longer seen as a competitive struggle for existence, but rather as a cooperative dance in which creativity and the constant emergence of novelty are the driving forces. And with the new emphasis on complexity, networks, and patterns of organization, a whole new science of qualities is now slowly emerging. Well, one of the most important recognitions in this new understanding of life is the recognition that networks are the basic pattern of organization of all living systems. As you know, ecosystems can be understood in terms of food webs, that is, networks of organisms. Organisms are networks of cells, cells are networks of molecules. So the network is a pattern that is common to all life. Wherever we see life, we see networks. It is important to realize that these living networks are not material structures. So when I say wherever you see life, you see networks, you can't actually see them. They are what we call functional networks, that is, connections between various life processes that form a network pattern. So in a cell, for example, these processes are chemical reactions among the cell's molecules. In a food web, the processes are processes of feeding, of organisms eating one another. And in both cases, the network is a non-material pattern interconnecting these processes. Closer examination of these living networks over the last 30 years or so has shown that their key characteristic is that they are self-generating. In a cell, all the biological structures, the proteins, the enzymes, the membranes, and so on, the DNA, are continually produced, repaired, and regenerated by the entire cellular network. Similarly, at the level of a multicellular organism, the bodily cells are continually regenerated and recycled by the body's metabolic network. So living networks continually create or recreate themselves by transforming and replacing their components. Well, this lies at the very core of the new understanding of life. And since a network is a pattern of relationships, it is evident that understanding life in terms of networks requires that we learn how to think in terms of relationships, in terms of patterns, in terms of context. And this thinking in science is known as systems thinking or systemic thinking. It emerged in Europe in the 1920s and 1930s from a series of interdisciplinary dialogues among biologists, psychologists, and ecologists. Ecology, of course, being a very new science in the 1920s. So from the very beginning, systems thinking has been an interdisciplinary effort. Well, in all these fields, scientists realized that a living system, an organism, an ecosystem, or also a social system, because as you well know, we have social networks. So a living system is an integrated whole whose properties cannot be reduced to those of smaller parts. The systemic properties are properties of the whole, which none of the parts have. So systems thinking involves a shift of perspective from the parts to the whole. For example, just to give you an example, if you ask yourself, what is stress or what is health? These are systemic properties. The stress of an organism is not the sum of the stresses of the molecule. The mass of the organism is the sum of the masses, but the stress of an organism is a systemic property. So to promote this shift of emphasis from the parts to the whole, the early systems thinkers coined the phrase, "the whole is more than the sum of its parts," which became sort of the slogan for this whole movement. Well, what exactly does this mean? In what sense exactly is the whole more than the sum of the parts? Well, the answer is relationships. All the essential properties of a living system depend on the relationships of the system's components with each other and the relationships of the system as a whole to surrounding other systems. So systems thinking means thinking in terms of relationships. Understanding life requires a shift of perspective, not only from the parts to the whole, but also from objects to relationships. And this is not very easy for us, especially not for those of us who were educated in science, because in science we were always taught that in order to be scientific, you have to measure something, you have to weigh it, you have to quantify it. And that even spilled over into the social sciences. There's, for instance, a well-known saying in management, what can be quantified, what can be measured can be managed. So what do you do with relationships? How do you manage relationships? You can't measure them, but you can map them. You can draw maps of how things are interconnected. So there's another shift that goes with the shift from objects to relationships. It is a shift from measuring to mapping. And you could also say it's a shift from quantities to qualities. Well, the early systems thinkers in the 1920s and 30s identified these basic concepts to describe living systems as integrated wholes. Concepts like organization, pattern, complexity, the idea of emergent properties, the notion of living systems as self-organizing, the concept of the ecosystem, and the associated notions of ecological cycles, food webs, and so on. So those are the basic concepts that we teach today when we teach an introduction to systems thinking. By the end of the 1930s, most of these key concepts had been identified and defined. Then the 1940s saw the formulation of actual systems theories. This means that the systemic concepts were integrated into a coherent conceptual framework, into theoretical frameworks describing the principles of organization of living systems. Now, when you look at the history of systems thinking in standard textbooks, you will find that the Austrian biologist Ludwig von Bertalanffy is commonly credited with the formulation of the first such conceptual framework, which he called general systems theory. And when you mention the term systems theory today, most people will, especially those in the history of science, will think about general systems theory. However, 20 to 30 years before Bertalanffy, before he published his first papers, Alexander Bogdanov, a Russian medical researcher, philosopher, and economist, developed a systems theory of equal sophistication and scope, which unfortunately is still largely unknown outside of Russia. Bogdanov called his theory tektology, from the Greek tekton, meaning builder, the same root as architecture, the master builder. So tektology can be translated as the science of structures. Bogdanov's main goal was to clarify and generalize the principles of organization of all living and non-living structures. Technology was the first attempt in the history of science to arrive at a systematic formulation of the principles of organization operating in living and non-living systems. It anticipated the conceptual framework of Ludwig von Bertalanffy's general systems theory, and interestingly, it also included several important ideas that were formulated 4 decades later in a different language as the key principles of cybernetics by Norbert Wiener. The stability and development of all systems can be understood, according to Bogdanov, in terms of 2 basic organizational mechanisms: formation and regulation. The dynamics of formation consists in the joining of systems, which he called complexes, in the joining of complex systems through various kinds of linkages which Bogdanov investigated in great detail. He emphasized in particular that a tension between crisis and transformation is central to the formation of complex systems. And in doing so, he foreshadowed the work of another Russian, Ilya Prigozhin, and Bogdanov showed how organizational crisis manifests itself as a breakdown of the existing systemic balance, and at the same time represents a transition to a new state of balance. And he not only did that, he defined categories of crises. And with that, he anticipated the concept of catastrophe developed in the 1960s by the French mathematician René Thom, which later on, under the name bifurcation, became a key concept of complexity theory. So Bogdanov's technology is really quite awesome, anticipating not only general systems theory in many details, but also cybernetics and even key aspects of complexity theory. Now let me come to another subject, the view of living systems as integrated wholes led some scientists of the late 19th and early 20th centuries to extend their search for wholeness to the entire planet and to see the Earth as an integrated whole, a living being. Now, of course, the view of the Earth as being alive has a long tradition. Mythical images of the Earth Mother are among the oldest in human religious history. Gaia, the Earth goddess, was revered as the supreme deity in early pre-Hellenic Greece. And this is why the modern scientific conception of our planet as a living system is known as Gaia theory. The term biosphere was first used in the late 19th century by the Austrian geologist Eduard Suess to describe the layer of life surrounding the Earth. A few decades later, the Russian geochemist Vladimir Vernadsky developed the concept into a full-fledged theory in a pioneering book titled Biosphere, published in 1926. Vernadsky saw life as a geological force which partly creates and partly controls the planetary environment. Among all the early theories of the living Earth, and there were quite a few, Vernadsky's comes closest to our contemporary Gaia theory. Well, the view of living systems as self-organizing networks whose components are all interconnected and interdependent was expressed repeatedly by the early systems thinkers. However, detailed models of self-organizing systems could be formulated only very recently when new mathematical tools became available that allowed scientists for the first time to describe and model the fundamental interconnectedness of living networks mathematically. The intricacy of these living networks defies imagination. If you take only the very simplest living system, which is a bacterial cell, you see that it is a highly complex network involving literally thousands of chemical reactions that go on simultaneously and are all interconnected. So before the 1970s, there was no way in which these networks could be described and modeled mathematically. But then computers came on the scene, and with powerful high-speed computers, scientists and mathematicians could develop a new set of concepts and techniques for dealing with that enormous complexity. And during the subsequent decades, in the 1970s and 80s and also 90s, these new conceptions coalesced into a coherent mathematical framework, popularly known as complexity theory and technically as nonlinear dynamics. It's called nonlinear dynamics because its key characteristic is that it is a nonlinear mathematics. So complex systems are nonlinear systems. You may have heard of chaos theory, you may have heard of fractal geometry. These are parts of nonlinear dynamics, of complexity theory. Well, the discovery of this new mathematics, these new nonlinear techniques, has led to major breakthroughs in our understanding of biological life, and is widely regarded as the most exciting scientific development in the late 20th century. One of the first scientists to apply complexity theory to the study of living systems was the Russian-born Nobel laureate Ilya Prigogine at the University of Brussels. Prigogine was intrigued by the fact that living organisms are able to maintain their life processes under conditions of non-equilibrium. And by this, he means thermodynamic and chemical non-equilibrium. In other words, in a living organism, there are always things going on. Energy and matter comes from the outside, in terms of food, is absorbed, there are structural changes, there's development, there's evolution, so there are always chemical processes happening, there never is a static chemical equilibrium. And Prigogine became fascinated by these systems far from equilibrium, and he asked himself, what conditions must exist for these non-equilibrium systems to maintain themselves? In order to solve the puzzle of stability far from equilibrium, Prigogine actually did not study living systems, but turned to much simpler chemical non-equilibrium systems, which had been discovered, and especially special chemical oscillations. And I just realized that there are another two Russian names here that I didn't write in my script. One of the best known of these chemical oscillations is called Belousov-Zhabotinsky reaction, after two Russian scientists who discovered it. Those are chemical cycles where if you have, for instance, molecules that, say, are red, have a red color, or generate a red color, and the other that generate a blue color, you will see spontaneous oscillations from red to blue and back to red, or you see spirals and so on. And this was discovered by Belousov and Zhabotinsky independently. So Prigogine studied these chemical systems in great detail, and the crucial breakthrough occurred for him during the early 1960s, when he realized that these systems must be described by nonlinear equations, that they are nonlinear systems. And so this fundamental recognition of the link between far from equilibrium and nonlinearity was the breakthrough for Prigozhin, and eventually he developed with his colleagues a nonlinear thermodynamics for which he got the Nobel Prize. And he called it the theory of dissipative structures, combining the notion of structure, which is something stable, and dissipation, which is constant change. Well, according to Prigozhin's theory, dissipative structures not only maintain themselves in a stable state far from equilibrium, but may even evolve. When the flow of energy and matter through them increases, they may encounter points of instability, known as bifurcation points, at which the system may branch off, and therefore bifurcate, branch off into an entirely new state where new structures and new forms of order emerge. This spontaneous emergence of order at critical points of instability, which is nowadays often just called emergence, is one of the hallmarks of life. It has been recognized as the dynamic origin of development, learning, and evolution. In other words, creativity, the generation of new forms, is a key property of all living systems. Now, Prigozhin's theory of dissipative structures has another important implication. Since all dissipative structures have the potential to evolve, and since not all dissipative structures are alive, like these chemical reactions that are dissipative structures, they're not living systems. They don't have cells, DNA, and so on. They're just chemical systems. So since evolution potentially occurs in all dissipative structures, this means that there must have been a pre-biotic evolution of dissipative structures before the emergence of the first living cells. Well, this view today is widely accepted among biologists, but it was radical when it was first proposed, and it was proposed by another Russian scientist, the chemist Alexander Oparin. Oparin stated boldly that life on Earth must have originated from inanimate matter via an increase of molecular complexity through a long pathway until the emergence of the first living cells. So he postulated a spontaneous and continuous increase of molecular complexity toward life. He illustrated his idea of molecular evolution with a speculative scenario in a seminal book, The Origin of Life, published in Moscow in 1924. Well, today there are several thousand scientists who specialize in this field, the origin of life, following the path and the basic ideas pioneered by Oparin. Well, I'm afraid I sort of rushed you through this with a lot of concepts, but I wanted to get the basic contributions of Russian systems thinkers into this very brief outline. And of course, there are more. I just mentioned the most important ones. So after this brief review, let me now return to sustainability. As I mentioned before, a sustainable community must be designed in such a way that its ways of life do not interfere with nature's ability to sustain life. And to do so, we first must understand how nature sustains life. Well, we need to move from biology to ecology here, because sustained life is a property of ecosystems rather than individual organisms or species. Over billions of years of evolution, the Earth's ecosystems have evolved certain principles of organization to sustain the web of life. Knowledge of these principles of organization or principles of ecology has become known as ecological literacy. In the coming decades, the survival and well-being of humanity will depend on our ecological literacy, on our ability to understand the basic principles of ecology and to live accordingly. This means that ecological literacy must become a critical skill for politicians, business leaders, and professionals in all spheres, and should be the most important part of education at all levels, from elementary and secondary schools to colleges, universities, and the professional training and development in all spheres. We need to teach our children, our students, and our political and corporate leaders, if you wish, the fundamental facts of life. For example, the fact that one species waste in an ecosystem is another species' food. So there's no net waste. Matter cycles continually through the web of life. The energy driving the ecological cycles flows from the sun. Diversity assures resilience, and perhaps most importantly, we must realize that life from its beginning more than 3 billion years ago did not take over the planet by combat, but by networking, by cooperation, by forming partnerships. Well, once we become ecologically literate, once we understand the processes and patterns of organization that enable ecosystems to sustain life, we will also understand the many ways in which our human civilization, especially since the Industrial Revolution, has ignored these ecological patterns and processes and has interfered with them. And we will realize that these interferences are the fundamental causes of many of our current world problems. Thinking systemically, we recognize that the major problems of our time are systemic problems, which means that they are all interconnected and interdependent. And to solve these problems, therefore, we need systemic solutions. We can turn around the interconnectedness of the world's problems to our advantage so that one action can solve several problems at the same time. Let me give you just one example, and that is agriculture. If we changed from our chemical, large-scale industrial agriculture to organic, community-oriented, sustainable farming, this would contribute significantly to solving 3 of our biggest problems. First, it would greatly reduce our energy dependence, because we are now using 1/5 of our fossil fuels, 20%, to grow and process food. The healthy, organically grown food would have a huge positive effect on public health, because many chronic diseases are directly linked to our diet. Diabetes, strokes, many forms of cancer, and so on. And finally, organic farming would contribute significantly to fighting climate change. Why? Because an organic soil is a carbon-rich soil. It's a living soil, a carbon-rich soil, and therefore draws down CO2 from the atmosphere and locks it up in organic matter. So this is just one example. Today, there are numerous NGOs around the world that have developed and applied such systemic solutions. They make it evident that we have the knowledge and the technology to build a sustainable future. What we need is political will and leadership. And this leadership, I believe, needs to come from 4 sectors of society: government, business, the academic world, and the global network of NGOs that constitutes the new global civil society. In my view, we shall be able to move toward a sustainable future only if all these sectors collaborate. Svetlana Chernikova dedicated her life to promote such collaborations between government, business, civil society, and academic scholars. And we can honor her best by continuing this work. Thank you very much.